Welcome to the ML in Production reading group. We're meeting to discuss Chapter 8 of Chip Wynn's book, Designing Machine Learning Systems. This chapter is on data distribution shifts and monitoring. So just looking at the table of contents here, the main kind of sections of this chapter are first just talking about what causes ML systems to fail, because the reason why we care about distribution shifts and the reasons why we care about monitoring and having observability for our ML system is because we want to stop it from failing. So it's important to take some time and think about what causes ML systems to fail. And then if we look at the things that specifically cause ML systems to fail, one of the big ones is basically the fact that the dependence on data and the kind of tight coupling between data and the model and the whole ML system, basically. So that leads us directly into the second section, which is about the ways data can change over time, and in particular, the fact that machine learning models without continual learning in them kind of make this stationarity assumption, this assumption that the future is going to be like the past. And that assumption is basically always broken in the real world, almost always. And so uh, we need to be able to extend our models to handle this non-stationarity of the real world, this change. So there's a big long section about different ways that data can change and the sort of like typology of ways data can change. That's a fun section. I'd love to talk about that more. Um, and then also how we detect it and how we address it. We don't fully go into the like true way to address data distribution shifts this chapter because that's the subject of its entire own chapter, which is continual learning, the next chapter. The final section then addresses how you actually get the information needed to know whether your model has failed and potentially what the cause is and how to fix it. So that's this final chapter on monitoring and observability, where monitoring means just like getting information out of a system, and observability means monitoring a system well enough that you can fix it without having to like take it out of production and recreate it. Um, so there's some neat connections that to control theory that are mentioned in that section, which is fun if you have that kind of a background to your machine learning. Okay, so that's kind of an overview of the chapter. Does anybody have a section that they really wanted to cover, that they really wanted to dive deeper on, dispute, or extend? If not, then we can just go through them basically in order and talk about the ideas that come up. So we'll start with causes of ML system failures. This one, I think, this is a really important section, and I think worth thinking about deeply. And there's also lots of really valuable links in this section to other references on system failure. Part of what makes ML engineering and software engineering an engineering discipline is a concern about failure, right? Like being a software developer or a computer programmer is different from being a software engineer, precisely, I think, because a software engineer cares about understanding system failures. So the there's like a long lineage of work on the causes of system failures. And this this section here on ML system failures first talks about these kind of like general software system failures. And I wrote a summary Twitter thread on a bunch of really great papers on this from sort of different engineering disciplines. So going back to like the design of databases and the sort of development of the ACID principle for transactions and the development of transactions for databases. And then also and then extending that all the way up through, cloud systems and how they fail and how they're designed. So in general, there's like we're all kind of familiar with the ways software systems can fail, like because we've run into them, triggered them ourselves, or run into them. Dependency failure Ran into that just the other day when I tried to update Flake 8 and found a fun dependency conflict. Deployment failure. Ran into that this week while I was deploying something to AWS Lambda. Hardware failures. Haven't run into that recently, but it does happen. It happens a lot at scale when you've got thousands of CPUs or GPUs or tens of thousands of hard disks. Lots of them break. And Yeah, so this section is a little bit less less directly interesting with ML, um, but this reliable machine learning by Todd Underwood, who also kind of wrote or gave a really interesting talk about um, ML systems, points out that really there's a lot of failures in a big ML system that are really just about distributed computing being really hard. So this is so it's important to understand these kinds of failures, even if you're an ML engineer who really only cares about the ML specific failures, because you've got site reliability engineers to help you with the rest of it. These are going to affect your system, and so you need to at least be aware of them. Any thoughts or questions on software system failures?
No questions here.
Gotcha. Yeah. Yeah, I think the what I liked about this section as a whole is that it nicely balances pointing out that these like software system failures are important and you need to know about them with recognizing that there are in fact ML specific failures and ways that ML models break that you need to address. Um, and that are not going to be handled for you by just general site reliability engineering. I think a lot of people tend to focus too much on one or the other. So the biggest one is training serving skew or production data differing from training data. I have been running into this recently. Just for example, some handwritten data, handwritten text images where the training data is white on a black background, but then most of the things that people are going to submit are probably going to be black on a white background. So these are the kinds of differences. If you aren't super clear about your data processing and production pipeline, these are the kinds of differences that can kind of sneak in and cause your model to not do well in production. Um, so anybody have any examples of running into this problem where the data they wanted to in the end apply their model on in production or in an application ended up being different from the training data?
I have the reverse case. I have a little issue with this section because when you train data, your target should, your labels should come from your training data distribution. I think like it's not like, when you start out, it should be the same because you're going to draw from the same part. Uh, and then your input data changes because like time changes or culture changes. But there's a reverse case where you have a target if you have your initial labels and then you want to try to use you keep the labels, but you try to add more training data by adding external sources that may not be the same distribution as your original training data or data set. And then it seems like it's just trial and error. You get a data set and you add it in and you see if it helps or not. And then there's I haven't seen much more after that. It's just, you want more data, but you can't afford, or it's much cheaper to get external data sets than to get it yourself. So you just put it in and see if it helps or not. So that's the other, or like a compliment, I guess.
Yeah. Yeah. So I do think that there are, and we'll discuss this more as we go through the like detecting data distribution shifts uh and there just like aren't very many good strategies for improving models. It's still kind of like an unsolved problem. But jumping back to um the first point that you raised, Daniel, I think the production data differing from training data, in the ideal case, you draw training data that looks exactly like what you're gonna see in production, and there are definitely tons of cases where you can do that. Like, for example, if you're automating away something that is currently done by a human team, then you have data directly from the human team operating in production. And so you don't have as much to worry about. Like, and as you said, like, drift over time is maybe the only thing happening. But if you sometimes you want, like, if you're building an ML powered tool from scratch, you might not have any production data to work off of. Like, say you're Grammarly and you want to offer people like corrections and suggestions for the text that they're writing. Grammarly, like, now has lots of supervision and has production data. So they get feedback from users, and they have data that they've collected from what users have written. But before they launched, like, they didn't have that, and so you have to, and presumably they wanted to start off with their ML model, and like, so they needed to collect training data of text and corrections to that text, to, like, make it super simple. And that training data may differ from the production data. Similarly, if you use simulation, if you use augmentation, like, there are lots of different ways that you might break away from the training data looks exactly like production data. Um, and that's also sort of, even separate from things like data pipeline issues that I brought up. And so I do think there are ways other than distribution shift or drift, that your production data can end up looking different than your training data.
Oh, are you saying there's some task that you don't exactly have the data because it doesn't exist, but you could find a close enough derivative where the derivative data is good enough to do well on your new task. And then eventually when you get the real distribution, which is close to that derivative, then is that what you mean?
Yeah, I guess.
Okay.
Yeah, yeah, yeah. What I'm saying is that we often need to kind of we need to approximate what's going on in the real world with our training data, right? Like, no academic benchmark data set really comes from a production setting, like ImageNet, or even, or like Common Crawl, or even the, like, glue tasks. These None of these are really what the data is going to actually look like in production. Even like MNIST, right, which was successfully used to make, like, digit recognition software in the 90s. Like, there it is it was the MNIST data set is based off of a mixture of, like, Canadian high school students and US civil servants, if I remember correctly. And, your production data, what if you deploy that into a digit recognition system, unless it only ever, operate, or, unless it only ever operates on those specific people, then the production data might be different than the training data. And that's not the same as it changing over time. Does it make sense?
Yeah, that's fine. I, it's my gripe was like the, you can't trade, you can't have a model to work on some other data if it's not close to it. Because that's my only gripe. And when I read this part, it seemed like they're different and it's like if they're different, it's like comparing apples to oranges. You can't do it. So there's an assumption where it has to be a close to.
Yeah, I think that's right. I think part of this is that this all kind of falls under the rubric of generalization, which people don't have great frameworks for. Like, there's generalization in terms of, like, generalizing onto the same data set, new draws from the same distribution, where there's, like, lots of good mathematical work. But when people talk about models generalizing, what they really mean is something like, grokking or whatever, where the model actually learns an algorithm, that you wanted it to learn, or a concept that you wanted it to learn, that is maybe implicit in the data, but then will also be in other data sets that you draw from. And I think, yeah, the fuzziness of that concept is kind of infecting a little bit this, like the fuzziness of the concept of generalization is kind of infecting this section. One of the one of the scarier ways that ML systems can break is this degenerate feedback loop issue, which is if you like a lot of people talk about ML systems having virtuous cycles in them, which is you put the ML system out there in the world, then you gather more data based on the ML system's performance. Maybe you have labelers, or you get your users to provide labels for you, like CAPTCHA or Facebook's like face detection algorithm. You have users generate feedback for you, and now you can make a better model, which allows you to make more predictions, which allows you to get more user feedback. And it sounds like this nice virtuous cycle, but there are also these vicious cycles like these degenerate feedback loops. These come up a lot in reinforcement learning, where a reinforcement learning agent um, can, because a reinforcement learning agent actually effectively generates the samples from which it learns. It takes actions in the environment and then finds out what the rewards are. Reinforcement learning agents also have this tendency to get stuck in these kind of bad solutions, and to have these kind of like degenerate feedback loops. And so this, I think maybe we are actually all familiar with being on the receiving end of these degenerate feedback loops from using recommendation like systems that have recommendation systems behind using software products that have recommendation systems behind them. So, for example, like you click a couple of videos on YouTube, and all of a sudden, the YouTube thinks that like you're obsessed with teapots because you watched like 2 or 3 videos about teapots at one point. And now all your recommendations are for teapot videos by teapot influencers who just want to spend 20 or 30 minutes talking about teapots. And that like reflects the ways in which these systems tend to like over index on certain behaviors. And this is like risen to the point of being a like a critique people have of ML models even outside of the discipline, and sort of like a societal level problem around filter bubbles and echo chambers. So there's I think, 4 recommender systems. I don't have a ton of experience with recommender systems, so I can't comment on how well these methods actually work for them. But it is something that people are concerned about increasingly, and that people work on trying to resolve.
So in the section about fixing the degenerate loops, there's like a TikTok example where uh, they get a new video that's randomly assigned. Yeah, that chapter where it's randomly assigned to an initial pool of traffic, and then it's essentially crowdsourced. And then based on the crowdsourced opinions, they it seems like they elevate it to another hierarchy of crowdsourcing, like a bigger pool of traffic.
Mhm.
Have you seen that done? Do you know if that's like done at a lot of places? That seems like a pretty interesting idea. You randomize it and then you crowdsource it and then you kind of scale it by just moving up a hierarchy.
Yeah. So TikTok has a particular issue here because TikTok doesn't really have any user-based discovery in it. Like YouTube is there's like a front page of YouTube for one thing, and then people can like search YouTube really easily, and search is a very prominent component of YouTube. And then like people promote their YouTube videos on other channels, and that's like and those are all major ways by which YouTube videos get views. And then the recommendation system that where users get like videos recommended to them without search, as like autoplay videos, or in their like directly uh, like on YouTube's app as recommendations. Like those are not necessarily those aren't the only way that people find videos, or like they aren't the primary way that people find videos. On TikTok, it's almost exclusively algorithmic recommendation. There's no like public square of TikTok, and it's actually pretty hard or not really like straightforward to share like a link to a TikTok video. Um, it like it's and it's like as soon as you watch one video, it immediately starts trying to recommend like the video is like 15 seconds and it immediately starts recommending you other videos. And so the like recommendation system is the absolute core of TikTok. And so they have to be able to like recommend videos super quickly and at a super high quality. So I think that's one reason why they are so much more aggressive about this kind of stuff. Um, and it also helps that they their format of super short videos allows them to really quickly get this information because the video is only 30 seconds long. You can get 100 reviews in 30 seconds and you can expect like a pretty solid yield. If you send that out to 500 people, like maybe 200 of them will watch the whole thing. Whereas if the video is 30 or 40 minutes long, like some YouTube videos are, then it's going to take 30 or 40 minutes before you know whether people watch all the way to the end, for example. And so, like, TikTok's in a pretty TikTok both has doubled down on this and then also is in a pretty solid position to make use of recommendations.
Yeah, I mean, if you think about it, it could be, oh, we want to be able to adjust any data shifts really fast, so we're purposely going to set our videos short. To with I've never used TikTok, so whatever, 15 seconds or 10 seconds, and then that lets them do all this, get the best latency and be relevant to whatever's happening.
Yeah, yeah. Um, yeah, I think the maximum length is definitely longer than 15 seconds. I think it's 30 seconds or a minute or something. But yeah, but a lot of the videos are very, very short, 15 seconds, 20 seconds. And yeah, they take a ton of advantage of it. And then so they both I think there's a couple things. One is like there's the pure recommendation system aspect of it, which can be done like without paying any attention to the content of the video. But then also TikTok, I think, does a ton of like deep learning uh powered stuff where you actually try and understand what's in the content of the video and use that once they've done this initial like completely random assignment, then I think that they use more like they use content based algorithms to be like, oh, this appears to be a video about teapots. So we're going to start recommending it to people who like videos about teapots.
Okay.
I think, yeah, there's a ton of interesting stuff there. I've read like one or two articles about TikTok, but I don't know how much of what they do is like public knowledge. So it's a little bit. There's some of it is people taking pot shots in the dark, like I was just doing, on what they think is going on. Yeah, they talked about positional features and like sort of trying to take into account the some of the most egregious forms of feedback loop, where whatever you put at the top is most likely to get clicked on. So maybe you should like take that into account when building your model. Sort of treat it as a covariate is how you would put it in statistics, and try and pull out the effect of which position something was ranked in before you decide whether that was a successful recommendation because of the content or just because of its position. Okay. So now we're on the data distribution shift section, unless there's anything else anybody wanted to say about um,
Uh,
feedback loops
I'll
and ML
just say,
filter failures.
I'll just say one point on that last table about the
Mm.
positional feature. I mean, my takeaway was I didn't think about this before. It's like you're adding a bias variable in order to be able to debias it later. With that in the table, that first position, false, 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 true, true.
Mhm.
I thought that was a powerful idea because you can track its position and that might help the model a lot. But then when you use it in inference or whatever you're going to use it, you can just set the first position to false. And then that kind of can debias your model. All right, that's all I want to say.
Yeah. Yeah. That is an interesting way of thinking about it. Yeah, I think, yeah, one way, yeah, again, reaching for kind of like statistical ways of thinking. These are called like nuisance variables or covariates. So things that you know have an impact on the target value, but are not the like fundamental thing that you care about learning about. Um, and so it's like very common with when you design, say, an econometric study or a psychological study to try and come up with what the major nuisance variables are that might impact the relationship between the variable of interest and the output value and like track those so that you can control for those values. So I think in general, I think actually that this kind of there's a period over the last like 7 or 8 years where during the like deep learning revolution where everybody was like, oh, you don't need old school statistics anymore. You just use deep learning, like throw giant data sets at it and don't worry about these people asking you about correct parameter inference or causal modeling or all these other boring things that stats people care about. And I think like to a certain extent, there's been a realization that all those ideas actually are important in ML systems, and you do need to incorporate them and adapt them to work well with these more flexible models um, like gradient boosted trees and deep neural nets. And so even the simplest version of that, which is just including your bias, like a variable that you think might bias your model, and then like freezing it, or sort of like separating out into two models, one of which models the nuisance variable, one of which models the thing of interest. Like even those simple approaches can get you pretty far. I think this is also something that we're going to find with data distribution shifts, and just sort of in general with trying to determine whether our models are valid, when and where they are valid, what causes the models to be invalid, and how we can like extend them to make them valid over a larger domain. I think there are ideas from the world of contemporary ML that are useful around data distribution shifts, but I think there's also lots of other ideas in like model validity and in causal inference that are helpful here. This data distribution shift section goes over the different like named types of data distribution shift. So the general idea here is that the your model is learning stuff about the joint distribution of your inputs and your targets. And in particular, in general in machine learning, we learn the conditional distribution from the inputs to the targets. And our model outputs something like a conditional distribution over y given the inputs x. So over the targets y given the inputs x. And so the like that's very literal in the case of logits. So classification models, which most natural language models kind of look like classification models now. They like you produce this distribution over the outputs. Um, that's what your machine learning model is learning. And even in regression models that don't necessarily look like a distribution, there's usually some kind of like probabilistic interpretation of what the model is doing. So if it's trained by squared error loss, it's learning a conditional Gaussian distribution over y given x. Um, so just kind of a little bit of stage setting here, reminding us of what this joint and conditional distribution are. So the way that people came up with these like typologies of data distribution shifts is to break down this joint distribution that our model's operating on, this joint distribution of data and targets, and break it down basically using the two ways you can break down a joint distribution into its conditional and marginal. So the joint distribution, if you take these two things, by the way, these two ways of decomposing the joint distribution and put them next to each other, that's Bayes' rule, right? P of y given x times P of x is P of x given y times P of y. All you got to do to get the usual way people write Bayes' rule is to pull like P of x to the other side and say P of y given x is P of x given y P of y over P of x. So this is just like a basic fact about distributions, just like Bayes' rule. that tells us how, like, what the pieces are of them and how we can combine them together. And to get the different types of distribution shift, we say what happens when one of these is fixed and the other one changes. So covariate shift is when your input data changes, but the relationship between the input data and the targets doesn't change. Label shift is when the labels change, but the likelihood that goes from these labels to the data, so the relationship between the labels and the data doesn't change. And then concept drift is when this relationship here, P of y given x, the thing that your model's trying to learn, is changing, but the input distribution is staying the same. There's also a fourth option, which is when this value here, P of x given y, is changing, but P of y stays the same. So that's mentioned here in this footnote. So this like typology of distribution shifts is basically the only other option that you have is like everything is changing all at once. So you can have like all four of these things could all change, and that's happening, and the distribution is changing. So the reason why people came up with these particular types is because they want to kind of like pick out a specific, simpler way that a distribution can change and talk about how you can solve it if you know that that's the way that the distribution is changing. So this is like a breakdown of some like basic kinds of types of distribution shift. They can occur together basically if all things can also change at the same time. So there's a I made this little kind of oops, come on, there we go. I made this little Venn diagram to represent this. So the each of these represents which distributions are changing. So if you are in this section here, label shift, then you know that P of X given Y is not changing. So that's this gray circle here. So we're outside of the gray circle. And so all of these are types are label shift because X given Y is not changing, but Y is changing. And so there's some interesting things here, like certain types of shift can occur with each other and certain types can't. And you never, uh, yeah. And in the middle here, we have like all things are changing at once. Then I gave a name here to that type that's in the footnote, mechanism shift, for when P of X given Y changes, but P of Y stays the same. So there's this kind of like mathematical approach to thinking about these types of distribution shift. They're helpful because if you know that the data is changing in a specific way, then you can apply a specific tool to try and fix it. Unfortunately, this P of y given x and P of x given y, these conditional distributions, we don't get to see them really, right? Like we have to calculate them. And so like P of y given x is a typical machine learning model. P of x given y is like a generative model of the data. And so we don't, those don't come for free. So it's like not easy to be able to figure out, is P of y given x staying the same? I don't know. You can usually check whether P of x is changing and whether P of y is changing. You can check whether P of x is changing by looking at the data that you have. If you have labels, you can look at P of y and try and figure out whether P of y is changing. But you don't know what's happening with P of y given x and P of x given y. You don't know what's happening with the conditional distributions. And so that does make it kind of hard to use this like typology of distribution shifts to solve a problem that you're encountering in your production machine learning system. Any questions or comments on the distribution shift? With distribution shifts, the fundamental concern is that you want to know whether the metrics of your model are changing or whether the user experience for people using your model is changing. Um, so if you have labels, then you can just check whether the model's doing well in uh and sort of like check these metrics, right? And then distribution, you can guess maybe that it's due to a distribution shift. And then try and resolve that issue. But the real problem is that you generally don't have these access to labels in your production setting, right? Because if you did, then if they were easy to get and like immediately available, then you wouldn't really need your machine learning system, right? Because that you whatever your source of labels is could stand in for what your machine learning system is doing. Um, and so there's kind of um, an impasse, a Gordian knot of a problem here, where you um, you don't have access to the exact thing that you need in order to understand how your model is doing. So there's like heuristic methods like black box shift estimation, and there's some more principled methods like ML daemon, um, that try and detect distribution shifts and try and um, like balance the need for labels versus the cost of labels. But it's all very ad hoc and heuristic right now. So this is a place where there is still like lots of academic work as people try and come up with methods for solving this problem. But it feels like there's probably not going to be some like general purpose solution that just solves this for all possible problems and you just add it to your system and then you're done. So there's a discussion of how people detect distribution shift. There's a couple of different ways. So some people use statistical tests. So they'll track like the median or the variance or whatever statistic of their data that they care about, and then try and see whether that is changing over time. And the most general version of this for telling whether two distributions are different from each other is the Kolmogorov-Smirnov test or KS test, which looks at whether uh, the cumulative distribution function of the two things is different. It only works for one-dimensional data, as is noted here. Um, so um, that makes it tough because we often work with really high dimensional data. And also the KS test is very, very sensitive. It detects any difference in distributions, and many changes in distribution are very benign. Um, and so unclear how useful the KS test is. I think there's a link to Hamal Hussein um, gave a good lecture on why the like statistical based methods aren't super useful in the real world for detecting distribution changes.
I think that link is why the TensorFlow tool isn't that good. I don't know if it's specifically if statistics are not good. And
So
I
it
just speak for that tool.
yeah, so it's about TensorFlow Extended's tools, but like TensorFlow Extended's tools are these one-dimensional statistical methods. And so it's like there are other things about TensorFlow Extended that I think Hummel beefs about in that video. There was actually a kind of interesting paper that came out just this week. Um, Let me pull that up. That purports to so one of the ways that so covariate shift is I think the one where people um have the most interest. Um, and this is when P of X changes, but P of Y given X, so the relationship between the labels and the inputs has stayed the same. Um, so this is one that people have looked at quite a lot, because P of X changing, like you don't need labels to detect this. And so one recent, um, this is going to be at iClear. which is next week. Oof. Domino here uses cross-modal embeddings of your data uh, to try and discover like which parts of the data set your model is doing poorly on. So um, you like if you work with images, for example, they've learned to encode images in a way that encodes both like the image content of it, and also sort of like a natural language description of the image. And so if you find that your model does well on lots of types of images, but not sort of like a certain area of this cross-modal representation space, this model is able to say your errors are coming from this particular region of the cross-modal representation space, and not just, oh, here's like an embedding vector that's the centroid of this region of representation space. It actually explains the errors with natural language using this like natural language decoding. And so can say, in this example, your model is failing on pictures that have that are pictures of the sky that have no birds in them. Um, so yeah, so it uses these like encoders um, that are things like clip and video clip to encode things into this representation space. So you can these things are you don't necessarily have to train it yourself in order to get this if you're working on a widely used domain. So this is I haven't fully like worked through this paper and of course haven't used it myself. But this seems promising for some of these um as like kind of a model as an automated model auditing tool. I think there's probably no replacement for looking at what your model is doing well on um yourself and sort of like understanding your data and understanding your model. But this is a nice like automated tool to help scale that up.
Okay, I'll give it a couple years, see if it turns out to be true or not. It's a mature option.
Yeah, yeah. So super, super fresh. I would say like this would be something to if you are, thinking about this, thinking about model validity and thinking about covariate shift issues uh a lot. This is something to look into. But yeah, it's fresh, hot off the shelf research. So don't immediately deploy this into production.
Go back to the speaking of volatility, if you go back to the chapter, I guess I have a couple comments. There was a part where in the data distribution shifts where it talks about app ranking and where an app's rank may change between 11 and 100. I think it's on page 27 or something. It's app ranking. It's right before monitoring observability. Yeah. So the second paragraph and, or, oh, it's actually the top paragraph. Yeah. So I thought this was interesting where if you have this is where you have a variable and it sits between 1 and 100. That's how you have it categorized. And then it's very volatile. And if your model sensitive to the volatility of your uh, feature, you may want to kind of like do a course categorization of that feature. So in this example, they do instead of 1 to 100, they do 1 to 10 and then 11 to like they do. Sorry, the ranking here is 1 to like 10,000 or higher. So here they'll categorize it 1 to 10, put them in buckets 1 to 10, 11 to 1 app ranking. So 1 to 10, between 11 and 100, between 101 and 1,000. I thought like this I'm calling it like bucketing or bucketing averaging. I thought that was a pretty interesting idea to reduce volatility
Mhm.
in your models.
Yeah. And this is actually something for this came up a similar version of this idea actually came up when we talked about simulated data, which is that if you have simulated data, the tricky bit is that you want the simulated data to look as much like the real data as possible. If your model only ever sees a coarse version of the data, right? So rather than seeing a full point cloud for a self-driving car, maybe, rather than seeing like a full color image, it only sees a point cloud, or maybe other rather than seeing a full point cloud, it sees some like simplified derivative of that, like a mesh. Then your simulated data only has to look right at the level of the mesh, right? It doesn't have to look right at the level of the actual like image that you're showing or the actual sort of like raw data. So in general, sort of coarse graining things is one way to um, like make your model less sensitive to distribution shift. Of course, that means you need to have. We're now getting back into the realm almost of feature engineering because you're trying to design the inputs to your model in such a way that the model can still learn from them, but it's not the raw data. So that's I think there's a bit of a trade-off there between like the expressivity and the capacity of the model uh,
Yeah.
and the robustness to shifts.
Yeah, it seems like you may want it's like you're regularizing or you're removing information to reduce the volatility of your prediction.
Yeah,
And maybe that's because you don't have enough data. Because if you had an infinite amount of data, I think the one to whatever 10,000 probably be the way to go.
yeah.
You're going to remove information. And then the paragraph below, which it, there's a there's like a paragraph about if you have a model that does housing prices, and if you have two different cities, the prices in the two different cities, this paragraph uses San Francisco and Arizona, might have the price might change at different rates. And if you use one model to do both San Francisco and Arizona, um, it might be you might have to update the model at the faster rate, which would be
Mm.
San Francisco. Whereas there's this suggestion, where to use two separate models so you can update them independently. I thought that was a pretty good idea, at least to
Yeah,
think about.
yeah. I think also in general, so one thing is, yeah, decomposing or sort of like splitting up models, but also decomposing models. There might be a model that requires a ton of data to train, but moves very slowly, right? Like these large language models can be trained very infrequently, like maybe once a year. And that, um, because they capture such broad features of language that they don't need they don't need to be retrained every single day or every single week. But then the like precise behavior of your users may like which things they're saying tend to correspond with whether they're a happy user or an unhappy user or what they're going to click next. Those might change really, really quickly. And so you can factor your model into a slow moving piece and a fast moving piece and make the fast moving piece really agile and quick to retrain. Maybe it's just linear regression or logistic regression on top of the slower moving model. And that way you can get some of the benefits of both having like a infrequently trained model with high capacity and a frequently trained model with low capacity. And in some ways, that's like a flexible and adaptable version of throwing out information um, in like we just discussed, right? So we talked about bucketing things, but in some ways, like something like GPT or BERT is doing a very sophisticated form of that to produce its final embedding vectors.
I mean, I took this paragraph, my highlight of this paragraph is like, it's a cost versus performance. It's like a business decision. Like you're the CEO
Mm,
and you're gonna, it's like, it's a cost versus performance. Like, are we gonna spend money to update this large data set? And
mm,
if so, how much better or gain are we gonna get? Then the other option is already use separate models, and it might just be just as good or say 1% lower, but it reduces their cost by 10x or something.
mm.
I mean, that was my like highlight of this part.
Yeah, yeah. I think in a lot of enterprises, this ends up being, yeah, basically a business decision rather than a modeling only decision. Yeah. Okay. So we didn't get to monitoring and observability. There's some interesting stuff in there, but it's 10 o'clock here in California, so we're actually already over time. I already have the chapter from Chip. It's in the Notion doc. You can find the link for chapter 9. So, chapter 9 is on continual learning. So, the ultimate solution to data sets that change over time is models that change over time. And so, continual learning is one thing that people see as a solution to some of the problems we talked about in this chapter. So, I'm looking forward to that. And I know Amon was as well. So, we'll talk about that next Saturday.